In this video, we're going to learn about monotonicity analysis in the context of engineering design optimization. First, we're going to go through what we mean by a monotonic continuous function. Then we're going to introduce this topic of monotonicity in engineering design optimization. Or in other words, how do monotonic continuous functions show up in engineering design optimization problems? Then we'll have an introduction to monotonicity analysis, which is an important tool for problem formulation analysis. And then we'll have several monotonicity analysis examples. We'll talk a few minutes about using monotonicity analysis for simulation-based engineering design optimization problems. And then at the end, we'll have a concept check to make sure that you understand some of the core concepts behind monotonicity analysis. What is a monotonic continuous function? In calculus, a function defined on a subset of the real numbers with real values is called monotonic if and only if it is either entirely non-increasing or entirely non-decreasing. Notice those specific words. We're using non-increasing instead of decreasing. We're using non-decreasing instead of increasing. That's a very specific choice of wording. Here we have a monotonically increasing function. As we increase x, f of x does not decrease. It does have a flat spot, however. This does satisfy the definition of a monotonically increasing function, even though we have a flat spot. Similarly, here is a monotonically decreasing function, whereas we increase x, f of x does not increase. It decreases over much of the domain, but we do have a flat spot again. Finally, here we have a non-monotonic function where we have regions where f of x decreases with x and increases with x. How does this relate to engineering design optimization? And what might happen if we try to solve an optimization problem involving monotonic functions? Let's talk about monotonicity in engineering design optimization. In a recent lecture, we talked about well-posed engineering design optimization problems, and this requires that a solution exists. There are a few important elements or requirements to be satisfied for a solution to exist. The problem needs to be feasible. That means there needs to be at least one point that satisfies all of the constraints simultaneously. And second, the problem must be bounded. In this lecture, we're going to delve into a little bit more detail regarding what we mean by a bounded problem. In engineering design optimization, monotonic relationships are very common. And so this is something that is important to know how to manage. Often, objective and constraint functions will monotonically increase or decrease with one or more design variables. In most cases, we are dealing with multivariate functions, and we do need to look at monotonic relationships of functions with respect to each individual variable. Here's one simple example of a monotonic function in engineering design. Suppose we are designing a structural tension member and we are using a very simple formula for axial stress, where axial stress is equal to the axial tensile load divided by the cross-sectional area. If we are designing this member and choosing what the section area should be, if we reduce the section area, that will monotonically increase stress and monotonically increase deflection for a fixed load. Monotonic relationships are often nonlinear. For example, here, if we're looking at load divided by area and we're changing area, this is an inverse relationship. This is a highly nonlinear relationship. It is very easy to conceptualize monotonicity in terms of linear functions, and in a lot of the simple examples we're looking at are going to involve linear functions. But in practical engineering design optimization problems, you will often find monotonic relationships that sometimes are linear, but often are not linear. It is the existence of monotonic relationships in engineering design optimization problems that drives the potential for unboundedness to exist. Let's look at a simple optimization example with a monotonic function. Let's suppose we are working to minimize 1 over x, but we're only considering positive values of x. If we were to visualize that, and we're staying over here on the right-hand side with positive values, and we'd like to minimize 1 over x, that's going to push us toward the right. If we have this constraint keeping us to positive values of x, and then we try to minimize this, we should ask the question, is this a bounded problem? Say if we were to either conceptualize walking downhill until there's no more downhill direction, or if we were to apply a numerical optimization algorithm to this problem, what's going to happen? What would you expect? Is it bounded? No, this is not bounded. We're going to keep moving off to the right toward positive infinity. What does it need to be bounded? We need something that's going to prevent us from moving off to the right. If we had an objective function that had curvature such that we have a local minimum, that would be one way. But suppose we're sticking with this same objective function. That's just the nature of this problem. We have this inverse relationship. But if we were to try to solve the problem as is, we're not going to get a bounded solution. What does it need to be bounded? If we are keeping the objective function, we need something that is capable of bounding x above. We need some constraint that prevents x from increasing without bound. Here's a simple way of doing it. Suppose we add a single bound on x. This is a simple linear constraint. We can visualize that here. Suppose we add that constraint. We're trying to minimize 1 over x. We're going to move downhill until there is no more feasible downhill direction. Here, at this point, where x equals 5, that's going to be the solution to this simple example problem. Let's ask a number of questions related to problem formulation analysis to help get us thinking about the bigger picture that we need to keep in mind as we are performing monotonicity analysis. One, we're interested in answering this question: is the problem bounded? Another question that usually is of interest is, would it make sense to transform the problem formulation into some other form? Sometimes it's possible to do this in a way such that the problem is what we call mathematically equivalent, or in other words, the two problems have the same solution, but the transformed problem is easier to solve. Maybe we've reduced nonlinearity. Another version of this is to reduce the problem. Maybe we find that there is some type of constraint activity or some way of using substitution to reduce the number of design variables and reduce the number of constraints in the problem. We're going to have an example of that a little bit later. We can use something like a change of variables or a change of coordinate system, whether it's a linear transformation or a nonlinear transformation. And sometimes these require a lot of creativity, but they can really pay off if it reduces the nonlinearity of the problem, or if it helps to improve problem scaling, which is something that we addressed recently. Another strategy is to see if it's possible to transform an optimization problem into a specific type of optimization problem that has particular solution algorithms that are very efficient. The whole area of what's called convex optimization or convex programming has many different classes of convex optimization problems with corresponding algorithms that are tailored to solve that class of problem. And if it is possible to transform your problem into one of these other convex forms, then that can be very advantageous. It can help you to solve your problem much more efficiently. Another type of transformation that's often helpful is if you have a problem where the analysis or the calculation of your objective and constraint functions involves some type of logical relationship. So, for example, if you have an if-then sort of statement somewhere buried within your objective function, that is a source of potential non-smoothness in the problem. And this is something that shows up often in engineering, especially in cases, for example, fluid dynamics. If you are analyzing a fluid system and for one particular design you have laminar flow, but then another design, it changes just enough that you transition into turbulent flow. And in that case, you need to use a totally different model. And there are other types of logical relationships that could be embedded within engineering analysis functions. And there's some tricks that could be used to convert these logical relationships to inequality constraints that are handled explicitly by the optimization algorithm. So if we can perform this conversion, then it's possible to produce a smooth problem that then is more easily solved using gradient-based methods that tend to be very efficient. We mentioned this concept just a moment ago. Will the result be mathematically equivalent? If we perform a transformation like this, two problems are mathematically equivalent if they have the same solution. Okay, these are just some questions to help get you thinking about the big picture, formulation analysis, and reformulation of problems. We're going to dig into monotonicity analysis as an important tool for this stage of the problem formulation cycle in engineering design optimization. Introduction to monotonicity analysis. This is a tool that can be used for a few different things, including assessing the boundedness of a problem. In the simple example we saw just a few moments ago, the 1 over x optimization problem, that was an unbounded problem. We could see that visually, graphically, but what if we have a problem that is higher dimensional? It's not something that we can easily visualize, or if it's based on some type of functions that are expensive to calculate. We would like to assess boundedness without having to perform visualization. This is a tool, monotonicity analysis is a tool that can help us do that. Sometimes monotonicity analysis can allow us to identify active constraints and reduce problem size through substitution. So this is known as problem reduction. We're going to have at least one example of problem reduction in a few minutes. Full monotonicity analysis is limited to analytical models or optimization problems where the objective and constraint functions are expressed in terms of things like algebraic expressions. But monotonicity analysis can still provide insights into more practical classes of problems, such as simulation-based problems or optimization problems that involve data-driven models. One of the big differences, though, is monotonicity analysis using these types of models will be an approximate analysis. We likely will not be able to prove anything, but it can still give us some insights, and it's often very worthwhile in performing as we're going through the problem formulation cycle. In this class, we're going to cover monotonicity in a somewhat limited way. It's going to be quite focused for the purposes of this class. There is a lot of depth behind this topic, so we're really only skimming the surface. We're going to focus on understanding problem boundedness, constraint activity, and conditions that can lead to ill-posed problems. If you want to learn about this topic in more depth, you can go to the supplementary textbook for this course, Principles of Optimal Design, Chapter 3, for a much more detailed treatment of monotonicity analysis. To sum up, monotonicity analysis is a very important type of formulation analysis that is a vital tool in your toolkit for design optimization. What do you need to know about monotonicity? First, what monotonic functions are. We already went through a brief description of those. How monotonic relationships can actually lead to a range of different problems with optimization, formulation, and solution. How the presence of monotonicity can actually be exploited to simplify optimization problems. How to recognize when solution difficulties are due to monotonicity issues, and how to resolve these issues. We may not, in this case, be able to prove anything about monotonicity, but going through this and understanding monotonicity conceptually will help you understand what things to look out for. What are the red flags that are clues that indicate you might have a monotonic relationship in your problem, and you might need to revisit the problem formulation to ensure that, for example, it is bounded. This is a historical technique when we're using it to solve problems completely. It is possible to apply monotonicity analysis in a way to actually completely solve some types of engineering design optimization problems. But in this class, we are primarily using it as an analysis tool. One way that it could be used in more general problems, say in cases where you have an objective function that is not strictly monotonic everywhere. Imagine a quadratic function, for example. If you were, however, to partition the design space, say of a quadratic function, into different regions, then each of those regions have monotonic behavior, and then you can apply monotonicity analysis to each one of those regions, and then there's a way of combining all of those results together as a strategy to actually help solve problems. This is typically not, at least in my experience, a super effective technique for practical scale engineering design optimization problems, but this sort of approach is important to understand, especially when it comes to giving insights that you need for formulation analysis. In this class, we're going to focus on the formulation analysis and conceptual understanding elements of monotonicity analysis. It's less vital as a solution tool, but it is an essential analysis tool. Here are a few definitions that we need to know for monotonicity analysis. Here I'm using the notation out of the Principles of Optimal Design textbook. This f of x plus indicates that we have a function that is increasing with respect to x. So it's monotonically increasing with respect to this particular variable. The partial derivative of f with respect to x is strictly greater than 0 for all x that are values of x within the feasible domain. Now remember, earlier we were talking about flat spots. Would this allow a flat spot? In this definition, because this is a strict inequality constraint, then this would not allow flat spots. The similar definition down here describes a monotonically decreasing variable. And we can say that x is a monotonic variable if either of the above is true. And this is a one or the other thing. What about the flat spots? If we have these conditions satisfied with inequality constraints that allow us to have the case where these partial derivatives are 0, then that allows flat spots. And the specific term that we use is this is weakly increasing or decreasing instead of being a strict monotonic variable. It's important to remember that monotonic relationships are different or can be different across variables. If we're considering a multivariate function, we need to look at each one of the input variables to that function to assess the monotonic relationships. Here's the Monotonicity Theorem. This is an important tool for detecting unboundedness. If a function, f of x, and the constraint functions, gi of x, where we have possibly more than one constraint, and here we're looking at inequality constraints, all increase weakly or all decrease weakly with respect to x, the minimization problem is not well constrained. So this allows for the definition of monotonic relationships where we can have flat spots. So this is a less restrictive requirement, and this is something that can very easily appear in engineering design optimization problems, especially if we have overlooked some sort of important constraint. If this is the case, there is no interior optimum and there are no inequality constraints capable of bounding f of x. So if we try to think about what's going on here, we have, here I'll sketch this out. Here we have a rough sketch of a decreasing or a monotonically decreasing function of x. Now suppose we have at least one constraint. Suppose g of x is an inequality constraint and we have posed our problem in negative null form. That means that wherever g of x is less than or equal to 0, the problem is feasible. And the way I've drawn g of x and f of x, these are both decreasing functions. This is something that satisfies what we described down here with the monotonicity theorem. If applying this assumption that we have this problem formulated in negative null form, then I can identify what the points or what the values of x are that are feasible. G of x is less than 0 to the right of this line, and it's greater than 0 to the left. So it's infeasible on the left, and this graphical illustration agrees with the theorem. If we're starting at some feasible point and we are wanting to minimize f of x, that's going to drive us to increase x, but there's nothing that's keeping us from going off to positive infinity. That said, if we had instead an interior optimum, if we had a local minimum that was a minimum not because of any constraints, but because of the shape of the function, then that would be a non-monotonic function. So suppose instead f of x, it curved back up. Well, then we could have an optimum, a minimum right there, but f of x then is no longer a monotonically decreasing function, and so the monotonicity theorem does not apply, and it is therefore consistent. We have this bounded problem over here, but we have this non-monotonic function. But if we have weakly decreasing or weakly increasing f and g, then that is an unbounded problem. Let's have a look at a first example. Here we have a simple linear function and two linear constraints. One is an inequality constraint, the other is an equality constraint. These are all linear functions, and that's going to indicate that these are all monotonic functions. There's no curvature anywhere in this problem. We're going to revisit this example a few times after we introduce some additional monotonicity analysis concepts, but we're going to have a look at a few things first. One, we can ask, well, how many degrees of freedom does this problem have? Well, this optimization vector x, it appears that there are only two elements. I see an x1 and an x2 in these functions and no other components. So we have a length of our optimization vector of 2, but we have this equality constraint. This removes 1 degree of freedom. So in this case, in this problem, we have just 1 degree of freedom in the optimization problem. And that indicates that maybe there is a way of simplifying this problem. Here we're going to first do some problem visualization and analysis. Then we're going to go back to some new monotonicity principles and then revisit this example. In this problem, we have two optimization variables, x1 and x2. The problem, as originally stated, is not in negative null form, so we may need to do some manipulation to make some progress with this problem. Here I've converted the two constraints to negative null form. Let's have a look at the gradient of the objective function. It's going to have two components because we have two optimization variables. The partial derivative of f, looking up here, with respect to x1 is simply 1. But x2 does not appear in the objective function, so the partial derivative of f with respect to x2 is 0. So this indicates that our gradient is the vector 1, 0. With this information, we can start to visualize what does the objective function look like. Let's sketch out some level sets of the objective function. It is not going to be changing at all in the x2 direction. So we're going to have level sets that are vertical lines. Suppose we want to get a sense of what direction is downhill. Let's have a look at a point in the design domain and draw the direction of the gradient. The gradient points to the right. That is the direction of steepest ascent. And then if we go the opposite direction toward the left, that's the direction of steepest descent. Let's start to construct what the feasible domain is. First, let's have a look at the inequality constraint. This is easy enough to visualize. It simply says that x2 must be greater than 2. So that means all of the values that are above this line where x2 equals 2 are feasible with respect to this inequality constraint. All of the points below this line are infeasible. Now we need to have a look at the equality constraint, and this is going to show up as a line in our optimization space. We'd like to plot this line because to stay feasible, we must stay on this line. One way of plotting this line is to solve for one of the variables x1 or x2 if we set h of x is equal to 0. I'm going to solve for x2. If we visualize this line in the x1, x2 space, we can see that it's going to look like a line that has a slope of 1 and an intersection with the x2 axis at -3. To stay feasible, we must be on this line where h of x equals 0, and we must also stay above this line where x2 is equal to 2. Suppose we have some starting point, an arbitrary starting point in the x1, x2 space. And if we are applying an optimization algorithm, a numerical algorithm, we are going to want to start with this point and maybe first find a feasible point. And then once we find a feasible point, then we can start to move in a downhill direction. This point that I drew, x0, it is not feasible. We are not on the h of x equals 0 line. So in the section on constraint optimization, we're going to be learning some techniques that can help us in this sort of situation where we have violated a constraint like this and moved toward a feasible point. Regardless of the specific method we use, suppose that we've found a point on the line that is feasible, that satisfies h of x, and now we want to move downhill. Now remember, if the gradient is pointing to the right, then downhill is pointing to the left. We have to stay on this line. Let's move downhill and see how far we can go while staying feasible. Once we get to this point that I've just drawn, we can see that there exist no more feasible downhill directions. This is a constrained optimum. We can see that this constrained optimum then exists at the intersection of these two lines where h of x equals 0 and right where x is equal to 2. Now we can do some substitution. If we say that x2 is equal to 2, Then we can go back and solve for x1 using our equality constraint, and x1 is going to be equal to x2 plus 3, so that's going to be equal to 5. So our solution then is x2 equals 2 and x1 equals 5. Now that we've visualized what this problem looks like in 2 dimensions, let's have a quick revisit of the definition of active constraints. This is something that we're going to need to know to move forward with monotonicity analysis. A constraint is active if removing it from the optimization problem changes the solution. In most cases, this means that when we have an active inequality constraint, these inequality constraints are satisfied with equality. Thinking about the metaphor walking down a valley and having to stay on one side of the fence or the other, and if this is a representation of an inequality constraint, if we're headed right up to the fence, or if we're at the fence, then that corresponds to satisfying the inequality constraint with equality. In the example we just looked at, the constraint, the inequality constraint on x2, that was active. It constrained us to be no smaller than x2 equals 2. And if we were to remove that constraint, then the solution would change. And actually, in this case, the problem would be unbounded if we did not have that inequality constraint, because we could keep finding new values of x that satisfy the equality constraint that continue to reduce f of x without bound. An inequality constraint is tight if it is satisfied with equality. This term tight includes all constraints that are active, but it's not equivalent to being active, because it's possible to have a constraint that is tight or satisfied with equality that is not active. We're going to discuss this issue in a lot more detail later in class when we cover inequality constrained problems. Let's now have a look at some tools for monotonicity analysis. Here's the first monotonicity principle. There's also a second monotonicity principle. We're not covering that in this class, but if you're interested in getting a comprehensive understanding of monotonicity analysis, you can learn this in the Principles of Optimal Design textbook. The principle is, in a well-constrained minimization problem, every increasing variable is bounded below by at least one non-increasing active constraint. Just reading it like this may not be that intuitive, but we're going to go through some very systematic examples based on this statement that allow us to analyze problem formulations in a very effective way. If only one constraint is capable of constraining a monotonic variable, that is an input argument to f of x, then we call that critical, and we can assume it is active. This is an important result. So for example, in the problem we just looked at with the bound on x2, that is the only constraint in the problem that is capable of bounding the problem. And so that is going to be a critical constraint. And a critical constraint is what's given by this definition here, and all critical constraints are active. Using the notation that we defined earlier, an inequality constraint g of x that's monotonically increasing can provide an upper bound on an objective function, and g of x that is monotonically decreasing can provide a lower bound. If we can identify constraints that are critical and active, this can help us to reduce problem size through a process known as substitution, or optimizing a variable out. And we'll have a couple of examples of this. Remember, all critical constraints are active, but it doesn't go the other way. Not all active constraints are critical. It is possible to have an active constraint that does not require, or that does not satisfy the requirement that we just described. A constraint could be active even though there's another constraint in the problem that is capable of constraining the problem. The first monotonicity principle can help us to identify oversights. For example, if we overlooked an important physical failure mode in a system, sometimes that will result in an unbounded problem. And this principle can help us detect that before we even go through a complete numerical solution. Also, it can help us to identify cases where we may have an ill-posed problem. Let's introduce one more definition. Here we're talking about constraint dominance. We can say that if for any point that is feasible in an optimization problem, any point x, if it is always the case that the actual value of a constraint, say g2, is strictly less than the value of g1 at the same point, and both of those points are less than or equal to 0, so they're feasible, then g2 cannot be active without violating g1 of x. Therefore, g2 is redundant and is dominated by g1. Because g2 is redundant, we can eliminate g2 from the formulation. This simplifies things. When we are solving a problem numerically, we have to keep track of which inequality constraints are active or not as we are moving through the design space. If we have fewer inequality constraints, that tends to improve computational efficiency. Here's an example. Here we're minimizing f of x equals x, so a linear objective function, and two linear inequality constraints. In this case, we can see that g2 of x is minus x plus 1. And if g2 of x is minus x plus 2, then g2 of x is always going to be greater than g1 of x. Therefore, g2 can be deleted. If we get rid of g2, then we're going to see it's possible to identify that g1 is critical and active through the first monotonicity principle. And if it's active, then we can say that g1 of x is equal to 0, and if g1 of x is equal to 0, then the optimal point is x equals 2. Let's have a quick look at a visualization of this problem. Remember, this is a single variable problem, and the objective function is simply f of x equals x. We would like to move downhill. If we had no bounds, no constraints on x, then this would be an unbounded problem. Let's have a look at what the two inequality constraints tell us. Here they are in negative null form. Let's modify these algebraically so it's a little easier to understand. The first constraint dictates that x must be greater than 2, and the second constraint dictates that x must be greater than 1. Let's have a look at what these two constraints look like. If we are looking at x must be greater than 1, then everything to the left of this line is infeasible. And if that was the only constraint that we had, then the bounded solution would be at x equals 1. However, we have this additional constraint that x must be greater than 2. And in this case, everything to the left of x equals 2 is infeasible. That includes everything that the first constraint that we looked at, x being greater than or equal to 1, cut off of the design space, and some more. So this constraint, x being greater than or equal to 2, dominates the constraint x being greater than or equal to 1. If we now go to minimize this objective function, we're going to hit this constraint first, and the constraint x being greater than or equal to 2 dominates the second constraint. Let's return to the first example. Remember, we have a linear objective function, a linear inequality constraint, and a linear equality constraint. We identified that this only has a single degree of freedom in the optimization space because of this constraint. And here, if we think of this as a substitution for x1, then we can take x1, or this replacement for x1, and plug it in to any place where we see x1, and that appears up here. So here we have x1 is equal to x2 plus 3 plus 2, or in other words, the objective function is x2 plus 5, and now the entire problem only depends on x2. Previously, we visualized this problem in a two-dimensional space. Now we can start to think about it in a one-dimensional space. Here, the objective function x2 plus 5 is plotted in this space. We also have this constraint that x2 must be greater than or equal to 2. If on the right-hand side of x2 equals 2 is feasible, and we want to go downhill, we want to reduce f of x, we need to go this direction, then we can keep going until we hit x2 equals 2, and then there exists no more downhill feasible direction. So therefore, at x2 equals 2, that is the optimal point. Now let's go back and solve for what x1 is. Knowing that x2 is equal to 2, we can then calculate that x1 is equal to x2, or 2 plus 3 equals 5. And then we can also calculate what the value of the objective function is at the optimum point. And that's going to be f of x is equal to 5 plus 2, or 7. Now we're going to introduce an important tool called a monotonicity table. This allows us to apply monotonicity principle number 1 to assess larger problems for both boundedness and also looking at constraint activity. It can allow us to sometimes even solve an entire problem, or more likely reduce the dimension of a problem without the benefit of graphical visualization. It also helps us to confirm when boundedness problems exist. It is possible for us to have a boundedness problem that is not discovered using the monotonicity table. We're going to go through a number of monotonicity examples here. We're going to start off with a number of graphical conceptual examples. And if you go back to the course notes on monotonicity analysis, these examples are found in pages 1 through 4. The next example involves problem reduction and problem solution. That's going to be found on page 5. And finally, we're going to look at an example where we are assessing boundedness, and this is found on page 6. Suppose we have a problem where the objective function is not monotonic. We have regions where it's either increasing or decreasing, and it's a function of a single variable, and we have a simple lower bound on this single variable. In this case, we can identify a few interesting things about this. It depends on what region we're looking at where we might find a local minimum. Here, far to the right of the bound, we see a local minimum, and it's because we have a non-monotonic function that such a thing exists. However, if we were to look farther to the left in the domain, then we can see if we were to start this direction, say if we're using a numerical solution method where we're trying to go downhill and keep going until there's no more feasible downhill direction, then we can see we can have a local constrained minimum right there. So if f is not monotonic, then we can have some additional scenarios where monotonicity analysis can't be applied. We could use a regional monotonicity analysis in this case. If we knew where to divide the domain such that f of x is monotonic in each one of those regions, then we could apply regional monotonicity analysis. If we knew to make a partition here and here, then in region 1, f is monotonically increasing in region 2, f is monotonically decreasing, and then in 3, f is monotonically increasing. This is kind of a cumbersome sort of approach to use a regional monotonicity analysis, but it's important to be aware that it exists and can apply to problems where we have non-monotonic functions, but that are regionally monotonic. Let's have a look at a slightly different case where we have a non-monotonic function, but it is an unbounded problem. Over here on the left, we again have a local constrained optimum. And in this problem, our objective function is not monotonic globally. But if we were to start over here with a descent algorithm, then we would just shoot off to a value where x goes toward positive infinity. So this is an unbounded problem. If we were to divide this into regions and perform regional monotonicity analysis, then we would discover in the right-hand region that yes, in fact, this is an unbounded problem. Let's go back and return to our substitution example. Let's go back to the stage where we have eliminated the equality constraint, and now it is a function only of x2. We have a linear objective function and a linear inequality constraint. Let's see how we can apply monotonicity analysis in a little more systematic way to this stage of the problem. We're going to construct what's called a monotonicity table. A monotonicity table has a column for each optimization variable, and it has a row for the objective function, and then it has a row for each inequality constraint. The basic idea is we want to identify monotonic relationships within the problem and then find out for each variable in the problem, in this case there's only one, if with respect to that variable the objective function is bounded. And to do that, we need to identify whether each of these functions are always monotonically increasing or decreasing with respect to each individual variable. In this case, we have linear functions, and that makes it easy because when we take the partial derivatives of these functions, they are constant. So the sign never changes. The partial derivative of f with respect to x2 is always positive. The partial derivative of g of x with respect to x2 is always negative. And going back to the monotonicity principle, if we have a strictly increasing objective function, or a monotonically increasing objective function like this, if we are assuming negative null form, then we must have a constraint function, at least one constraint function that is monotonically decreasing with the same variable. In other words, we need to have opposite signs in a single column corresponding to a particular variable. And if we identify these opposite signs, if there is at least one constraint that is capable of bounding the objective function, then we can say that it's bounded. But using the first monotonicity principle, if there's only one function, one constraint function that's capable of bounding the objective function, then we can say that this constraint is critical. And if it's critical, then it's active, and if it's active, then it's tight. Let's have a look at a few conceptual examples to understand this property in a little bit more detail. Suppose we have some other problem with a linear objective function and two linear inequality constraints. Remember, if we are assuming negative null form, then a point x is feasible if it simultaneously satisfies all of the constraints, and in this case that means that all of the inequality constraint functions must be less than or equal to 0. If we are looking specifically at g1, it crosses 0 right here, and then if we move to the right, the points are feasible with respect to g1. I can draw this bound, to the left, all of those points are infeasible. But if I look at G2, all of the points to the left of this line are positive, so therefore all of those points are infeasible. G2 dominates G1, thinking back to the definition we went through just a few moments ago regarding constraint dominance. Let's have a look at the monotonic relationships here. We could construct a monotonicity table for this case. F, G1, G2, X. F is always decreasing. G1 is always decreasing. G2 is always decreasing. Remember, if all of the functions are either decreasing or always increasing, then the problem is not well constrained. There is not a constraint that is capable of bounding f. And we can see this graphically if we were to start at a feasible point, say over here to the right of where G2 crosses 0. Then this would be the objective function value. Oh, sorry, that's not the objective function value. We have to go down farther for that. Go down here, here's the objective function, and we would keep going down without limit. X would approach infinity as we try to minimize f of x. Here is a slightly different example. In this case, f of x is a nonlinear function, but it is monotonically increasing. At least that's what I intended when I sketched it. And g of x is a linear function that is monotonically increasing. If we look at g of x, it crosses 0 right there, and to the left, g is negative, so that's feasible. Everything to the right of g of x is infeasible. And again, if we're just looking at this graphically, suppose f of x continues up like this, and if we start at some feasible point, x, and then here's f of x, and we move downhill, if f of x is monotonically increasing, then if we try to minimize it, x is going to approach negative infinity. Let's have a look at the monotonicity table for this case. Here we just have f and g, one column x. F is monotonically increasing, g is monotonically increasing. So both functions are increasing. This problem is not well constrained. Let's look at another conceptual example. Suppose we have a nonlinear f of x and a nonlinear g of x. G of x crosses 0 right here. It's positive to the right, so all of those points are infeasible. F of x is monotonically decreasing with x. Suppose we start at a feasible point and we try to move downhill. Eventually we'll get to this point, which is a constrained minimum. In this case, g of x is capable of constraining f of x. This is a well-constrained problem. We can construct the monotonicity table to verify. F is monotonically decreasing with x, g is monotonically increasing with x. We have opposite signs. G, therefore, constrains f. It's the only constraint that's capable of constraining f, so it is critical and active. So far, all of these simple conceptual examples have been functions of one variable. And if that's the case, the boundaries of the feasible domain are simply points. I want to point out this distinction. As soon as we move to more than one dimension, the boundaries of the feasible domain become a little bit more interesting. Suppose we have a function of two variables, x1 and f2, and the elliptical level sets I've drawn correspond to an objective function, f of x. And let's suppose right here in the middle, this is where we have an unconstrained minimum. But what if we have some constraints? Suppose we have some linear inequality constraints. One way we've learned about representing linear inequality constraints is using a matrix inequality. And if we have 4 constraints, say corresponding to this matrix inequality, then that is going to correspond to 4 half spaces in the x1, x2 space. If we take all of these half spaces, combine them together, and look at what points are feasible with respect to all of those half spaces, then we're going to get our feasible domain. Suppose that each one of these lines corresponds to the case where ax equals 0 for one of the 4 constraints. Further, suppose that inside of each of these lines, this polyhedron, that these are the feasible points. And so, therefore, all of the points on the outside, these are infeasible. And the boundary of our feasible domain is no longer just a couple of points or 1 point, but it's an infinite set of points that traces these lines. If we happen to have inequality constraints that were nonlinear, then these lines, these boundaries, would no longer just be straight, but they might have some curve to them. I mainly wanted to highlight that when we switch from these really simple one-dimensional examples to higher dimensions, then there's more richness to the problem, and we need to be sure to think in terms of the higher dimensional space. Now let's have a look at a somewhat more involved example where we cannot just simply visualize the monotonicity relationships in the problem. Here we're going to look at a problem with 3 optimization variables, and then we're going to see how a monotonicity table is actually quite valuable as soon as we start moving to higher dimension problems. It is useful for problems that are even higher than 3 dimensions, and in those cases we really cannot visualize what's going on with the problem, but with a monotonicity table we can assess things including boundedness and sometimes constraint activity. Here we have a problem with 3 optimization variables, 3 linear constraints, inequality constraints, and we're also told, we're given the specifications for the sign of these constants a and b, and those are going to be important in assessing this problem. And with this problem, we can't really visualize it because it is in 3 dimensions, or at least it's a little bit more difficult. But let's try to construct a monotonicity table and see if we can learn something from it. We might not be able to learn everything at the first try with the monotonicity table, but we might learn a few things that then allow us to keep moving and gain additional insights. We have a column for each one of the optimization variables. We have a row for the objective function and each one of the constraints. Again, we're looking for monotonic relationships. I have purposefully used linear functions to make this easy so we can at least get the main concepts here. If we have linear functions, then the partial derivatives are constant everywhere in the optimization space. If we look at x1 first, let's see, f of x, the partial derivative of f of x with respect to x1 is positive. It's everywhere positive. And g1, with respect to x1, that's everywhere negative. But then with g2, that's negative. And then g3, that's positive. If we have a look at the signs here, it's clear that f is going to be bounded with respect to x1, but it's not clear whether it's g1 or g2 that's active. Either one of those could be the active constraint. With this set of information, we really can't say anything about the activity of g1 or g2. Let's have a look at x2. F is monotonically increasing with respect to x2. And then if we look at the constraints, we can see that only g2 depends on x2. It's monotonically decreasing with respect to x2. In all of the other slots under x2 where there's not a relationship, I leave that blank. That indicates we have missing, either we have missing information or there's not a relationship. With x3, again, for f of x, we have this positive monotonic relationship. And then we see that only g3 depends on x3. And the partial derivative with respect to x3 is negative. We can identify a couple of things now. With x2, only g2 is capable of bounding f. So therefore, g2 is critical and active. Same thing with x3. Only g3 is capable of bounding f with respect to x3. So g3 is critical and active. If we know that constraints are active, then we know they are also tight, or they're satisfied with equality. And if they're satisfied with equality, then we can do some algebraic manipulation and potentially do some substitution. Because G2 is active, according to the monotonicity table, I can write that x1 plus x2 is equal to b. And if I look through this problem, I can see that there's an x1 plus x2 term. I can simply replace that with b. And because we have utilized G2 in the substitution, we can eliminate that from the problem. I'm going to rewrite this now so it's a little bit more clear. We have dropped both x2 and g2. I've also written out that the optimization variables are explicitly just these two, x1 and x3, to make sure it's clear. The original problem dimension, or the number of optimization variables, was 3. Now it's 2. We were able to reduce the problem dimension because we identified one of the constraints as active. Now let's have a look at what results by identifying that G3 is active, because it's the only constraint capable of bounding f with respect to x3. If that's the case, then we can say that 2x1 is equal to x3, or I could solve for x1 and say that x1 is equal to 1/2 times x3. And then any place I see x1 in this reduced formulation, I can replace that with 1/2 x3. If I go ahead and do that and perform simplification, the resulting formulation is this: minimize b plus x3 with respect to x3, subject to g1 of x3, that's the only one left, equals a minus 1/2 x3, and that must be less than or equal to 0. By identifying a second active constraint, we have been able to use another substitution to reduce the problem dimension further. Now there's only one optimization variable. That was as much as we could learn from the first monotonicity table that we formulated. Now that we've simplified it, I wonder if there's something else we can learn. Let's construct a new monotonicity table for the simpler problem. Here we only have x3. F is increasing with respect to x3. G1 is decreasing with respect to x3. And because of that, we can identify that G1 is active. And if it's active, then it's tight, and we can perform substitution yet again. We can say that A is equal to 1/2 x3, or x3 is equal to 2a. If we go back and substitute this value for x3 into the other two relationships we identified through constraint activity, then we can solve for the optimal value of the optimization vector x, and that's going to be a, b minus a, 2a. And then if we plug that in to our objective function, which is simply the sum of all of the variable values, that's going to be equal to b plus 2a. Through this iterative process of constructing a monotonicity table, substitution, and problem reduction, we have actually completely solved this problem. This is not always possible for optimization problems. It's nice when it is, but even if it's not possible to solve a problem using monotonicity analysis, it provides a lot of value. It can help us to identify boundedness problems, and it can also help us to reduce a problem partially. Let's have a look at one more example. Here we have, again, a linear objective function and a single linear constraint, a linear inequality constraint. And down here we've defined the sign of these coefficients a, b, c, and d, and that's essential for us performing the monotonicity analysis because we need to determine the signs of the partial derivatives here. Let's go ahead and construct a monotonicity table. If we do it by function, if we look at f first, then the partial derivative with respect to x1 is positive, and also the derivative with respect to x2 is positive. Now if we look at g1, it depends only on x1. There's no information about x2. g1, we have this negative relationship. C is less than 0. Because of that, the partial derivative of g1 with respect to x1 is negative. If we look at the first column, x1, we can see that g1 is the only constraint that is capable of bounding f1. We have these opposite signs, so we are at least bounded with respect to x1, and we can say that g1 is in fact active for this problem. However, f is monotonically increasing with respect to x2, but there are no constraints that even depend on x2. There are no constraints that are capable of bounding this monotonic objective function in the direction of x2. This means we have an unbounded problem. This is something we need to avoid. This example is an analogy to a practical design optimization case where maybe you've overlooked something. Maybe you've overlooked a failure mode that could be an inequality constraint that would be capable of bounding the problem, or maybe you've overlooked some physical phenomenon that could change the objective function from monotonic to non-monotonic that is capable of having an interior optimum. So, for example, if instead f of x looks something like this, and maybe one of the constraints looks like this, then we have a nice interior optimum, but if instead the function was monotonic, then it would be an unbounded problem, and we'd need something to bound it from up above. When going through the problem formulation cycle, it is very helpful to incorporate constraints that are limiting the design space that correspond to something that is meaningful in the design problem. If we add a constraint for the sake of bounding the problem, but it's, say, just a simple variable bound and it has no physical meaning, then that can be problematic. And if that bound that we've added in becomes active, then that's what we call an active arbitrary constraint. And active arbitrary constraints are another type of big red flag that there's something up with your formulation. If we think back to where that constraint came from, it came from the human designer who is formulating the problem. It was a subjective human decision if it's not directly linked to some type of engineering failure mode or some other type of external requirement. So that's why I call it an arbitrary constraint. If we add in an active arbitrary constraint to bound the problem, and that constraint is active, then that's an indication that there's something being overlooked as well. And so we need to do more digging. We need to figure out, is there some type of physical phenomenon that could make our objective function non-monotonic? Or is there some other type of failure mode that can fully constrain or help us to fully constrain the problem, but links to something that's physically meaningful and is not just arbitrary? Here I am going to add a simple bound, but I'm using this as an analogy. This bound represents a physically meaningful constraint. As we're going through this kind of analysis, if we find that there is some unboundedness along a particular direction with respect to a particular variable, then that can give us some insights into what type of physical failure mode might be important. What is something that's capable of bounding that particular variable? Think about what that variable corresponds to in the actual physical system design. Is there some kind of failure mode that will be triggered by changing that design variable? Here I am adding a simple bound on x2. This is a lower bound on x2, and the partial derivative of g with respect to, or g2 with respect to x2 has a negative sign. If I add g2 to this formulation, and we have two constraints, then g1 is capable of bounding f with respect to x1, and g2, I needed to add that to a separate line, is capable of bounding f with respect to x2, and these constraints are both critical and active, and then we could actually solve this problem through substitution. Let's address a few additional monotonicity topics. One is dealing with monotonicity in the context of optimization problems where one or more of our functions, our objective or constraint functions, requires a computer simulation. Instead of some type of nice analytical expression, an algebraic expression, instead we have to run a numerical computer simulation to get our function values. And in this case, monotonicity analysis may not be quite so straightforward. How do we do this when our problem is simulation-based? Sometimes these simulations really are black boxes. We know what the inputs are, we can get some outputs, but maybe we don't really know what's going on in the inside. In some cases, we can do an approximate monotonicity analysis in simulation-based design optimization. And this is something that may especially be motivated if we have gone through a full cycle of the problem formulation cycle. We've come up with the formulation, we've constructed the models, we've implemented the optimization problem, we've gone to solve it, but then something indicates that our problem might not be bounded, or there's some other issue that comes up that indicates the root cause might have something to do with monotonic relationships. If that's the case, we need to do a little bit more digging. And one thing we can do is do some sampling of the design space. Even if we cannot completely prove a monotonic relationship across the entire design space for a particular input-output relationship, we can still get some approximate information about it. Maybe we explore the design space at evenly spaced intervals and look at how the function changes, whether the objective function or constraint function, depending on what we are investigating. And that can help reveal the nature of these functions, even if it does not give us a complete picture. If we identify through this approximate analysis that there might be some monotonic relationships that could be problematic in the formulation, then that's an important clue. That's going to help put us in the right direction to figure out what we need to dig into. What variable is resulting in the unboundedness, and what potential functions might be failing to bound the problem. So if this happens, we need to, again, think about, well, what's going on with the actual physical design problem? Is there something that we're overlooking, whether another failure mode or some physical phenomenon that could be showing up either in the objective function or constraint functions that would change the monotonic properties of these functions and potentially the boundedness of this problem? So we need to do some digging that gives us the insights we need to know where to look, and we can be more strategic with our time instead of just guessing at what things might be causing the unbounded relationships. The topic of simulation-based design optimization is a rather important practical engineering design optimization topic. Here we're only touching on it. It really is beyond the scope of SE 413. If you are interested in learning how to apply design optimization to problems that are simulation-based, I would encourage you to continue your study. There are more advanced courses that you could take, or if you're interested in graduate school in design optimization, this is something that you can study more deeply. Now that we've gone through and looked at monotonicity analysis, how it relates to engineering design optimization, formulation analysis, and other aspects of the problem formulation cycle, let's take a step back and let's think about a number of the considerations we've made regarding problem formulation. This will help us to see how monotonicity analysis fits into the bigger picture. There are a number of things, a number of decisions that we're making along the way in problem formulation. If we're looking at things that are independent variables, these are things that often are inputs to our models, and we are often deciding whether these should be design variables or fixed parameters in the problem. That pertains to the design representation element of the problem formulation decision space. There are a lot of different performance metrics we might be interested in, and sometimes it's a little uncertain whether it makes sense to specify a performance metric either as an objective function or a constraint. In cases where we have a performance metric that has a clear threshold value, something like a temperature constraint or some other failure mode, where as long as we satisfy or we stay on one side of a limit or the other, as long as we satisfy the constraint, we're good, and there's really no value to be had in going farther away from the constraint, then that is a performance metric that really only makes sense to include as a constraint. If we include something as an objective function where there's really no value added by minimizing or maximizing it, then that really doesn't make sense in an engineering design optimization problem formulation. In cases where we have multiple performance metrics that do not have this sort of threshold property, and we want to either minimize or maximize all of them, then it might make sense to formulate a multi-objective optimization problem. Creating models that map our designs, as specified in the design space, to our objective functions and constraint functions is a critical part of the problem formulation cycle. Learning how to create models that are specifically useful for design optimization is a really important skill. There's a difference between creating a model that is good from an engineering analysis perspective and one that is good from an engineering design perspective. There are standard model validation strategies that essentially boil down to addressing the question, how accurately does my model predict reality? That's a different question from the utility of a model with respect to design optimization. In that case, we are interested in a model that helps us to accurately determine the best design. And that could be different. We are less interested in globally how the model does in predicting reality. We are mostly interested in, is that model going to direct us to the best design? We've talked about boundedness and monotonicity. These are things that arise all over the place in engineering design optimization. It's just the nature of the physical systems that we are focusing on designing, especially when it comes to failure modes with a threshold limit. And then also, it's very common with objective functions to have some type of monotonic relationship. We've discussed well-posedness. We need to have problems that are feasible. There's at least one point that satisfies all constraints simultaneously, and we must have a bounded problem. These two properties are essential for us to have a problem that has a solution which is needed for a problem to be well posed. We've discussed problem dimension, including how many degrees of freedom a problem has, which relates to how many design variables or optimization variables we have, how many equality constraints we have, and if we can identify active inequality constraints, we can use that to reduce problem dimension through substitution. We've talked at length in previous lectures about different types of scaling we can perform that can, in essence, transform our original formulation into a new problem formulation. This is actually a much broader topic. We often are interested in adjusting our problem formulation in ways such that it still gives us the optimal design that we want to get, but reduces the computational effort or difficulty required to get it. So we've talked about linear scaling techniques, both for design variables and objective and constraint functions. But there are other more general change of variables strategies that we can use to transform a problem into one that is easier to solve. We've talked about algorithm choice and, in particular, the two-way coupling between problem formulation decisions and solution method decisions. If we're using optimization as our solution method, algorithm choice is one of these decisions, as are all of the different decisions we have to make regarding algorithm settings. Let's go through a quick concept check, focusing on monotonicity analysis. First, see if you can answer to yourself, what is a monotonic function? If you're not sure, please go back and review. Why might monotonicity be an issue with engineering design optimization problems? 1. Functions are often monotonic, usually linked to the physical nature of the problems. For example, failure mode constraints. If we have monotonic relationships in a problem, it brings with it the potential to have unbounded problems. What is monotonicity analysis? This is a formal assessment of a problem formulation to check both for unbounded variables and critical constraints, which we can then identify as active constraints. How might monotonicity analysis be useful? Well, we can check whether a problem is well bounded. If it's not well bounded, it's going to indicate we've probably overlooked something, but it's not just a binary thing. It doesn't just tell us that, yes, we've overlooked something. It gives us some important clues. It gives us rich information about, with respect to what variable are we unbounded, what constraints are involved. We need to think deeply about the relationship between the unbounded variable and the different types of failure modes that variable could be connected to. We can reduce problem dimension through substitution. once we identify critical and active constraints. We can develop very rich intuition for what it takes to create a well-posed problem. In addition, as we gain experience with monotonicity analysis, it helps us improve our skill in problem diagnosis. For example, if we're thinking about going through an entire problem formulation cycle, where we've formulated the problem, implemented the model, and gone and solved or attempted to solve the optimization problem numerically, and we discovered something didn't happen right. We had an algorithm termination that did not result in a local optimum. And we have some other numerical clues that resulted from the solution. If we have a good understanding of monotonicity analysis, that's going to help us do a better job of sifting through the information we get from the problem solution and identifying a potential root cause. How might we perform monotonicity analysis on high-dimension problems? We looked at several low-dimension problems where we visualized the effects of different monotonicity relationships. But what about problems where we have more than 3 optimization variables and we can't visualize the problem? This is where the tool of a monotonicity table comes in. It allows us to assess monotonicity for problems of arbitrary size and determine whether monotonic variables are bounded. That's the end of our coverage for monotonicity analysis. I hope this was helpful in understanding this important formulation analysis tool. Thank you.